A star's life begins in darkness, in an optically opaque molecular cloud. Shielded by dust and gas from both galactic starlight and cosmic ray, the cloud cools, and the densest clumps of molecular gas, gravity overcomes internal pressure, and the clumps begin to contract. As you can see on the next slide, where the clump, starting out about 3/10 of a light year in size, begins to collapse, and gravity pulls it in, and the internal pressure from the cloud, proportional to temperature, pushes outward. And so it's the cooling of the cloud that allows the cloud to collapse, because at that point the central pressure becomes low enough so that gravity overcomes that pressure and the process of star formation can begin. These cold clumps are spinning as well as a result of tidal interactions in large molecular clouds out of which the clumps form. The spinning, collapsing clumps produce, first, a prestellar core, second, a circumstellar disk, and third, an outer, flattened envelope. This is illustrated on the next slide, where you see an artist's conception of a spinning clump, and in the next slide, you can see the collapse of that clump. There's the infalling envelope. The next is the disk, in which material is transported inward toward a stellar seed. That is, the seed out of which a fully grown star will form. Next. Now, this is a very dynamic process in that the gas is transported from the collapsing, rotating core onto the disk and then transported inward to the stellar seed. The mass of the star increases over time. To build a star similar to the Sun takes about 1 million years to transfer the material from the infalling envelope through the disk to the core. The accreting material arises from regions that rotate around the central star. And in fact, if all that material were to fall onto the central star, absent any other mechanism, the central forming star would soon begin to spin so rapidly that it would kick material off the equator, and the star would no longer be able to build up its mass. And so nature provides another mechanism which allows stars to form and build up to their full mass. And that is the action of jets or wind that carry away some of the angular momentum from the spinning material in the accretion disk. These stellar winds and jets act as regulators of angular momentum that keep the central star from spinning up so rapidly that it's no longer able to accrete material. An artist's conception appears on the next slide. Here we have the infalling envelope, and we have the accretion disk. The accretion disk is carrying material onto the central star, and in order that the star not spin up too much, there's a wind or jet that emanates from the inner regions of the star disk system and carries away the spin angular momentum of the material from the accretion disk, thus allowing the star to build up mass. An artist's conception of the situation is shown on the next slide. Here you can see the protostar at the center, the rotating flattened accretion disk around the central star, and the outflow that emanates from the inner regions of the disk. It's the disk around the star from which planets take form. Lower mass planets are formed by the agglomeration of tiny micron-sized grains which over time stick to one another and build up mass until they create a swarm of kilometer-sized planetesimals. Planets are built up of collisions, as a result of collisions between these kilometer-sized planetesimals. Larger planets, planets similar to Jupiter, the largest planet in our solar system, may have been formed in one of two ways. First, it's possible that they formed very rapidly early on in the history of the accretion disk as a result of gravitational instabilities in which a gas giant planet formed within 10 to the 4th or 10 to the 5th years. The next possibility for forming a Jupiter, and the one most likely to be the case for the Jupiter that formed in our solar system, is again agglomeration of micron-sized dust grains into kilometer-sized bodies, collisions leading to the production of an Earth or several Earth mass body, which attracts gas from the surrounding disk to build up the gaseous envelope of Jupiter, a process that might take on the order of 1 million years or perhaps a bit more. Which mechanism accounts for the formation of a Jupiter probably depends upon the initial mass of the accretion disk and the initial surface density of the disk, that is, the mass per unit area in the disk. Let's look at the next slides. Here is an artist's conception of formation of a planet via rapid gravitational instability. In the lower right-hand side, you can see evidence of that's found in a numerical simulation in which gravitational instability led to the formation of a Jovian mass planet on the order of 10,000 to 100,000 years. In the next slide, we see the buildup of larger bodies via collisions between kilometer-sized so-called planetesimals. On the left, we see a swarm of planetesimals. In the center, we see the buildup of a few bodies. And on the right-hand side, we see the beginnings of a more mature solar system in which larger mass planets, including perhaps Jupiter, take form. So, to summarize, we start out with a molecular cloud shielded from galactic starlight and cosmic rays, cooling over time. Clumps within that cloud, rotating clumps within that cloud, form infalling envelopes, accretion disks, and stellar seeds. The stellar seeds build up mass over time as material from the accretion disk moves inward and adds mass to the central stellar seed. And also in the accretion disk, planets begin to form as micron-sized grains agglomerate into kilometer-sized planetesimal bodies, and collisions between those planetesimal-sized bodies lead to the formation of larger bodies like Earth and like Jupiter, and perhaps in a few disks, Jupiter-like planets form very rapidly through gravitational instabilities. Over on the order of several million to 10 million years, the formation of solar systems is done, and the system is close to the mature system that we see today. It's a delight for me to be here in Taiwan, both to visit my colleagues at ASIAA and also to have met the director and his staff at the Taiwan Astronomical Museum. And I want to thank my colleagues at both institutions for inviting me to Taiwan and for providing the opportunity to speak with faculty, students, and also to speak to the public, both through my astronomical research and through my photographs. Thank you very much.